My name is IBM, and today I would like to introduce alternating current. Just we shall be comparing alternating current to DC just precisely, but basically the unit is called alternating current. Do not forget to watch the solved past paper questions to get more confidence. I'll attach links for the past paper questions in the video description, or I'll attach links to the solved past paper questions, the video promotion. So you can always watch the solved past paper questions after watching the tutorials for alternating current. Okay, let's go. So this is the Cambridge International Education. So today we are actually going to deal with a paper. We are actually going to deal with the alternating current, and I think this is going to be lesson number 1. This is going to be lesson 1 of alternating current, and I think and I hope that this is going to be of use or of help to everyone who is watching this video. So without wasting time, I would like to take you to what we really expect to cover in this unit. This is the course outline of this topic. We expect to explore characteristics of alternating current. When we talk about characteristics of alternating current, we may talk about peak values, root mean square values, and so on and so forth. Those are the characteristics. We shall talk about transformers briefly. For examination starting from 2022, you may not find transformers there, but because transformers use alternating current, so I wanted to blend the ideas of transformers to alternating current. Then we shall also briefly talk about transmission of electrical energy, the same thing you mentioned in IGCSE, and the same thing you mentioned in IGCSE. For example, why power is transmitted at high voltage. Then we shall also talk about rectification, where direct alternating current is converted into direct current. So let's briefly go into what we expect under the characteristics of alternating current as the first thing. So all along in our study, we have dealt with systems in which a battery is always connected to a circuit and there is a steady current in one direction. So that means we have been referring to direct current most of the times. So we are much familiar with systems in which a battery is connected to a circuit and there is a steady current in one direction. And that is what we call direct current. However, most of the domestic electricity supply produced by domestic electricity supply is produced by generators, is actually the one which uses alternating current. Most of the domestic electric supplies produced by generators at a power station is one which uses alternating current. And by the way, most of the devices that we use at home use DC, but what is supplied is actually AC. The devices use DC. But what is supplied at power stations such as dams or hydroelectric power is actually AC. So while DC electricity flows in one direction through a wire, alternating current alternates. As the name stands, it alternates, it keeps changing direction. So alternating current alternates its direction in a back and forth motion, as we shall explore in more details. So you might be asking yourselves, what is very special about this alternating current? Before we go into what is special about alternating current, the domestic power supply is generated at a rate of between 50 to 60 times per second. In other words, the frequency of alternating current which we use at home is between 50 and 60 times per second, or 50 to 60 hertz, which depends on the country. Some countries generate it at 50 hertz, some countries generate it at 60 hertz, depending on the consumption needed. So what is special about alternating current? We shall explore what is special about alternating current. But one important thing we need to notice is that alternating current is created by alternating current electric generators, and it is the generators which determine the frequency. Just like any other wave, electricity or the alternating current wave, its frequency is determined by the generator itself. So it is possible for countries to generate electricity at a rate of 50 to 60 times per second because they can just design a generator which oscillates or which generates a frequency of about 50 to 60 hertz. And the frequency of any wave depends on the frequency of the generator. So that's what we shall be exploring under characteristics of alternating current. So let's start with the characteristics of alternating current in more details. Before we go into the characteristics of alternating current in more details, I want to explore what is very special about alternating current. So you may ask yourself, what is very special about alternating current that direct current cannot be used, or that direct current is not popular? Of course, we are used to batteries, and most of us should be aware that batteries are cells, those are producing DC. But like I have mentioned, that most of the devices we use at home, ranging from the refrigerator, the TVs, everything at home, most of them use direct current. But the power supply that we receive in our main supply, or in our main switch, or in our main circuits are actually alternating. So how are they able to become this? How are the components, the refrigerator, able to use DC? Yet what is supplied is actually AC. We shall explore that in more details. But what makes alternating current special is that it can easily be changed from alternating current to DC. So that makes it even easier. Or that makes it to have several applications in everyday life. So alternating current or current electricity can easily be changed from AC to DC. So the special thing about AC is that the voltage can be readily changed, thus making it more suitable for long distance transmission than the DC. That's a very important fact. It can readily be changed. What do we mean by changing? Changing could mean raising its value, that is stepping it up, or lowering its value, that is stepping it down, as we shall mention later on. And we shall see that electrical power is normally transmitted to long distances after it has been stepped up, or after it is transmitted at higher voltages. And we shall see why high voltages later on under transmission of electrical power. And not only that, I've also mentioned that using several capacitors in the laboratory, inductors, using several electronic circuits, we can convert alternating current to direct current so that we can use it in a wide applications, or we can use it in so many appliances at home. Therefore, alternating current is extremely very special. We can easily step it down or step it up Stepping it up, we step it up normally for long distance transmission because there's an advantage. And we can use several other circuit components such as capacitors, inductors to mention but a few, so that we convert alternating current to direct current, which is used by most of the appliances at home. Of course, it is not possible to convert direct current back to alternating current. So that makes alternating current very special. So in our definition of alternating current or definition of AC, we shall define alternating current as an electric current that periodically, when I talk about periodically, it means over a certain specific period of time. An alternating current is an electric current that periodically reverses or changes its direction in the circuit with a frequency that depends on the source. So I said in some countries, alternating current is generated at a frequency of 50 hertz. I think that is most of the countries. In other countries, electric current or alternating current is generated at a frequency of 60. So it depends on the country's demand. So they design generators or alternating current generators which generate alternating current at different frequencies depending on what the country wants. So what makes alternating current alternating? What is actually alternating? If you recall your knowledge of AS physics and your knowledge of IGCSE electricity, you mentioned that current is the rate of flow of charge carriers. So we can think about what the charge carriers are in the electrical wires as being electrons. For alternating current, these electrons must be moving back and forth, back and forth. In the process, they are performing what we call simple harmonic motion. Our next topic is going to be simple harmonic motion, I think. So when we talk about alternating current, it comprises of the electrons which are actually moving back and forth, back and forth. In the process of doing so, they're actually transferring energy in the first place, and therefore they are performing what we call simple harmonic motion. Of course, simple harmonic motion, like we shall see later on, it is actually a periodic type of motion. And periodic means it keeps repeating itself over a specific period of time. That's why we shall call it periodic. So the current varies like a sine wave. Because it's back and forth, it will vary like a sine curve or a sine wave. If we compare the graph of DC to the graph of AC, we would observe that for DC, it is a straight horizontal line because the current remains constant. The current remains constant and it is steady throughout. If you connect a battery or a cell in a circuit, you expect a steady flow of current. But for alternating current, because it's back and forth, we say the electrons are oscillating. So if an electron moves towards and comes back, it makes one complete cycle, which can be represented by this first part of the graph. Going and coming back to form one complete cycle. That's what we are calling a sinusoidal, or they vary like a sine wave, a sine wave. So precisely we describe alternating current as being sinusoidal. In other words, the variation will follow a sine wave because the electrons are believed to be moving back and forth, performing what we call simple harmonic motion. Remember, if the electrons are oscillating back and forth, one complete oscillation will be equivalent to one complete cycle, and therefore that back and forth movement, if it periodically continues, then we can represent it with a sine curve like this one, which is demonstrated here. So for the first graph, we have direct current. For the second graph, we have alternating current. So at some point, the electrons move in one direction. At some point, the electrons change direction. So that means the current is going to be both positive and negative, unlike the direct current, which is only in one direction, flowing from the positive terminal of the battery to the negative terminal of the battery. For alternating current, it keeps changing direction, flowing from one terminal will be positive for the first half cycle, then the other terminal will be negative for the next half cycle, and they keep swapping signs as the cycles continue. Yet for a DC or direct current, one is permanently positive, one is permanently negative, and therefore current flows from positive to negative. Yet for DC, first half cycle it may be flowing like this, second half cycle it reverses direction. That is for alternating current. That's the difference. So we describe this kind of current as being sinusoidal. Sinusoidal is of course coming from sine. Okay, so we are still exploring and understanding the characteristics of alternating current. So because we have explored and agreed that the current is sinusoidal, and of course remember the current from DC values that we mentioned in electricity, current is directly proportional to V. If the current is sinusoidal, it also means the voltage is sinusoidal. Because from Ohm's law, if you remember, V is equal to IR. If the current varies sinusoidally, then it means the PD is also going to vary sinusoidally. It is going to follow a sine wave. Therefore, the alternating current and the voltage will have almost similar equations. And because it's following the sine curve, then the current, alternating current, is given by I naught sine omega t, and the alternating voltage is given by V equals to V naught sine omega naught. What are these quantities? I is the current at that particular time. I naught is the current when t equals to 0. And omega is still going to carry the same meaning as it did in, or as it does in circular motion, simple harmonic motion, and other topics. It is going to be called the angular frequency. Then t is of course the time at that particular moment. So I naught is later on going to be called the peak current or the maximum current. Then V is going to be the voltage at that particular time. V naught is going to be the maximum voltage or the peak voltage. Of course, omega and t are still carrying the same thing. I want you to recall from what we mentioned in, or what you will mention in simple harmonic motion and circular motion, that the time t taken for one complete cycle of, say, an electron moving back and forth is going to be called the period. That is the time for one complete cycle of the SC in this case, since we are dealing with alternating current. We are familiar with the term period from other topics and from AS. And if you recall, from circular motion, the period is going to be given by 2 pi over omega. And of course, we know that in circular motion, your teacher must have proved the y period is 2 pi over omega. Time for one complete cycle, maybe I can prove this briefly for you. Y period is 2 pi over omega. So in circular motion, the linear speed v is equal to omega times r. That is in circular motion. And the time for one cycle t is going to be distance divided by the speed. One cycle can be modeled to be a complete circle, and the distance around the complete cycle is the circumference of the circle, which is 2 pi times the radius of the circle. And if the speed or the curvilinear speed is omega times r, so I just divide this by r. So if r cancels out, it means the time for one complete cycle is 2 pi over omega. And the omega is said it is the angular frequency. So the time for one complete cycle will always be taken to be 2 pi over omega. Of course, do not forget concepts of waves. They will also apply here. If I know the period, the frequency can be taken to be the reciprocal of the period as shown here. The reciprocal of the period can be the frequency. And of course, the units are still the same. We know that frequency is the number of complete cycles per unit time. How many cycles does the alternating current have per unit time? Like I mentioned earlier on, that some countries generate alternating current at a frequency of 50 hertz. That means 50 cycles per second. And in some countries, they generate alternating current at a frequency of 60 hertz. That is 60 times per second or 60 cycles per second. Therefore, the units for frequency are going to still be the same units that we used in our waves. That is the hertz. And of course, 1 hertz is 1 cycle per second. So sometimes my students always write 1 hertz as being equal to 1 per second. So the frequency is the same as, the frequency has the same units as those of waves because it's still frequency. A few things we need to note here are the terms we shall always refer to. For example, the peak voltage. I said V naught is going to be the peak voltage, I naught is going to be the peak current. So the peak value of the current or voltage will be represented by I naught or V naught, and these are called the amplitude of alternating current. And of course, we know amplitude is the maximum. So it is the maximum current or the maximum voltage in that case. That's what we shall call the peak voltage and the peak current. Those are the amplitudes. Then another term we need to note very carefully. Sometimes we shall be referring to the peak to peak, from one peak to another peak. If this is a graph showing the alternating current, so what we mean by peak, this is the peak, which is I naught, and at the bottom we have another peak, which is now going to be negative I naught because this is alternating current. So when we talk about peak to peak, we are referring to this value here, which is twice I naught. Because this is I naught and this is I naught, the peak to peak is going to be twice I naught. Or if it is a graph of V against time, it is still going to be twice V naught. So the peak to peak value is going to be mentioned sometimes. Therefore, these are some of the characteristics of alternating current. So we have mentioned it has peak values, it has angular frequency, it varies sinusoidally. We have talked about period and we have talked about the frequency. So you must have noticed from the figure that we sketched above of alternating current that the average value is going to be 0. I think this makes sense. If you look at a graph of current against time for alternating current, it seems like the average is going to be 0 because if this is I naught and this is negative I naught, it means to find the average of, because the other one is above and the other one is below, it means the average is going to be just a value which is along the x-axis. So the average value is equal to 0 for alternating current. The average value for alternating current is 0. So you must start asking yourself a question. How does alternating current flowing in wires cause the wire to warm up? Of course, warming up means that there is heat dissipated in the wire, which means there is power dissipated in the wire. So how, if the average current in a wire where alternating current is flowing is 0, so how is it possible that there is heat generated or heat wasted in the wire that the wires become warm? We are going to address that shortly. So however, it doesn't mean that when alternating current is connected to a resistor, there is no power generated. This is not true. It does not mean that there is no power generated. So there is power generated even when the average current flowing through a given resistor is 0. So now the question is, where does the power come from? I want you to distinguish alternating current from DC. If DC, the DC current, of course the average value of the DC current, there's nothing like average value of DC current because DC current is steady and constant. But for alternating current, it keeps fluctuating. At some point is in one direction, another point reverse direction. So one direction positive, the opposite direction negative, it means that the average is going to be 0. But for DC values, it is just a constant current. So the power dissipated in a DC when DC current flows is obvious. And we saw that for that DC values, power was given by I squared times R because R is a constant and the current was a constant. So the power dissipated was a constant in a resistor if we had direct current. But in alternating current, the power dissipated may not be constant. However, it doesn't mean that there is no power even when the average current is 0. So if we consider alternating current in a wire, remember I have mentioned we can think about alternating current as electrons moving back and forth. And in the process of moving back and forth, these electrons are colliding with each other, and they are colliding with ions, with other ions or the atoms of the wire. In the process, the electrons pass on some of their energy to the ions or to the atoms in the wire. Therefore, they lose some of their kinetic energy to these atoms or to these ions, and therefore we expect that the vibration of the atoms increase, which means thermal energy is going to be dissipated in the wire. I want to remind you of the DC values that you mentioned in IGCSE and AS physics. From DC values, like I have mentioned, the power generated in a resistor is either given as I squared R, or it can be given as V times I, or V squared of I. These were if the current was DC. These were the DC values. These relationships apply to the DC values. If I use the equation V equals to IR directly, I'm referring to I as being direct current, so V is direct voltage. But remember, we are dealing with alternating values. So, since for alternating values, we have said that I equals to I naught sine omega t, then it means if I use the DC values or the DC formulas, I must modify them to incorporate the alternating values. For example, for power equals to I squared times R, the I is not going to be direct current. It is instead going to be alternating current, which is given as I naught sine omega t. So if I make such a substitution, therefore, where there is I squared, I put the value of I as I naught sine omega t because this is alternating current, then it becomes I naught squared R sine squared omega t. Now, if you're a mathematician, you notice if I try to find the average power on both sides, on the left-hand side, I naught squared is a constant, so and R is a constant, so it means I will only be finding the average power, the average of sine squared omega t, because t varies, therefore sine squared omega t is going to vary. But the average value of sine squared omega t is going to be a half. If you're a mathematician, you'll agree with me that the maximum value of sine theta is +1, and the minimum value of sine theta is -1. So sine of theta varies from +1 to -1. But if I square sine theta, it is going to vary between +1 squared is 1 up to -1 squared is 1. So it means I have 1 to 1. So it means the average is going to be 1 divided by 2, because if I square this, it is going to be +1 to -1. This is still 1, which is going to be the maximum. So that means the minimum is going to be 0 when t is equal to 0, then sine squared omega t is going to be 0. So it means the minimum is going to be 0. I want to repeat this for those who don't do math, because so I'm saying sine theta varies from +1 up to -1. That is how sine theta varies. Or I can say it varies between +1, 0 to 0 up to -1. I want to write a good statement here for those who don't do maths. So sine theta varies from +1 to 0 to -1. But then when I square and I try to find sine squared theta will vary between +1, because I'm squaring +1, then I square 0, it still remains 0. Then I square -1, still becomes +1. So it means if I consider sine squared theta, the maximum is +1 and the minimum is 0. So then what is the average? Of course, the average, I'm adding two quantities, +1 plus 0 divided by 2. So the average value of sine squared theta is going to be 1 divided by 2 mathematically. You can argue this in another mathematical language that you may want to consider. So what I'm saying is that if I try to take the average of the average power, we shall see that the average power in the resistor is not 0, even when the average current is 0. So the average power is not going to be 0. And by the way, someone will notice, but I can be negative. Remember, this is I naught. I naught squared is a constant. And because I naught squared is always positive, it means the average power will never be negative. The average power will never be negative. Sine squared omega t will always be positive. The average value of sine squared omega t will always be a half mathematically. So this means the power is always positive. The power is always positive. So what I'm saying is this: since I naught squared and sine squared omega t are always positive, it means that the power P is always positive. So we don't expect negative power in alternating current, even when the average current is 0, even when the current keeps changing direction, is both positive and negative. The power will always be positive. So that means if I am tempted to sketch a graph of power against time, it will always be above the x-axis. A graph of power against time will always be above the x-axis. If you try to sketch a graph of power against time, you don't mind about the negative part because the power will always be positive. We can even verify using the second equation, V power equals to V times I, and see if the graph of power against time will always be above the x-axis because the power is always going to be positive, whether the current is negative or positive. So the average power, if the power is always positive, it means the average power can never be 0. And if the average power can never be 0, it is enough to tell us that there is always power dissipated in a resistor when alternating current flows through it. So I am saying the power at a given time t for alternating current is given by that. Power is equal to I naught squared R sine squared omega t. So that means it varies. It means it varies. But the power will never be below the x-axis because sine squared theta is always positive in the first place. So it means the power is always going to be positive. I naught squared, the square of a positive or negative number is always positive. So I naught squared is also going to be positive. So even if the current goes below the x-axis, the graph of power against time will never go below the x-axis. We are still exploring characteristics of alternating current. So I want you to also note that from this equation, power equals to I times V, we can also verify that the power is always positive because remember from Ohm's law, V is equal to I times R. That means V is directly proportional to I. So if V is positive, I is going to be positive. If V becomes negative, I is always going to be negative because V and I change sign at the same time. They are always in phase, if I'm to use that term from waves. So V and I are always in phase. They change sign together. If V is positive, I is positive. The product is positive. If V is negative, I is negative. The product is still going to be positive. So this means the power will always be positive. So if I substitute these two into the equation, for example, I'll have that power equals to where there is I, I'm going to put the equation for alternating current, which is going to be I naught. That is I naught sine omega t times V. The equation for alternating voltage is going to be V naught sine omega t, which means the power is going to be I naught V naught sine squared omega t. So the power, if I use that equation, the power can also be given as I naught V naught sine squared omega t. If I take you back to the previous equation, which we had, and it was power equals to I naught, it was I naught squared R sine squared omega t. We saw that the maximum, we could see that the maximum power here, maximum power is going to be obtained when sine squared theta is equal to 1. And when this is equal to 1, it means the maximum power, which I would call P naught, is going to be equal to I naught squared times R. In a similar way, the maximum power here occurs when this part here is equal to 1. So it means the maximum power P naught is going to be equal to I naught times V naught. So I naught V naught is going to be the maximum power, or the peak power during alternating current flow. And of course, this equation is for instantaneous power at any given time. This one is also instantaneous power, that is power at that given time. So we now know we can derive the maximum power from that equation, or we can derive the maximum power from this equation here. I want you to relate these to the DC values. Remember, when it is direct current, I would simply say P is equal to IV. If it is alternating current and I say I naught times V naught, I'm finding the peak, the maximum power. And if it is DC, I would say power is I squared R. If it is alternating current, I'm finding the maximum power when I multiply I naught squared times R. I can't find the maximum power by multiplying I squared times R. It must be the peak current. Okay. So what I've been explaining is this, that the maximum power is I naught times V naught, but I'm saying it is also I naught squared times R if we know the value for the resistance. And the expression P equals to I naught squared R sine omega t, which we derived earlier on, would give us what we call the power at any point, at any instant, or we can call the instantaneous power. And by that way, you can also think about the other equation for power from DC values, that is, power equals to V squared divided by R. But remember the V, if we consider alternating voltage, V is going to be equal to V naught sine omega t. But this should be squared because V is squared, then divide this by R. So the power here is going to be equal to V naught squared sine squared omega t, and this is divided by R. So it means we can also argue that the maximum power P naught, because maximum power occurs when sine squared omega t is equal to 1. So it means P naught can also be V naught squared divided by R as the maximum power. Okay. So we now know the maximum power, then we should be talking about the average power, because we said the average power in the resistor is not going to be 0. So the average or mean power is the most useful quantity in alternating current because it is responsible for the heat dissipated in the resistor. So what do we mean by this mean power? The mean power is the quantity which must be considered or which must be used in assessing the power generated in the resistor, because the power varies from 0 to a certain maximum. Therefore, since it varies from 0 to a certain maximum, it is better we take the average power. So the average power is very, very, very important. I want you to recall that the quantity I naught, which we call the peak current, the resistance of the resistor are always constant or are going to be considered constant. But P is going to depend on the sine squared omega t. And I have said sine squared omega t has its average value as being a half, and I've showed this mathematically how the average value of sine squared omega t is a half. Alternatively, you can use symmetry. If you sketch a graph of sine squared omega t, you will notice that the graph is always going to be above between a maximum, which is 1, and the x-axis. If I try to sketch a graph of sine squared omega t, I think the graph would be like this. To be above the x-axis, because the negative part, when squared, it becomes positive, which means the average, if the peak is here and this is 0, so if this is 1 and this is 0, the average is going to be half of this peak. The average is going to be a half of this. So it means the average value of sine squared omega t is a half. That is, the graph either side is half. So we must now start thinking of the fact that the average power is really not going to be 0, because if the average value of sine squared omega t is a half, and yet I naught squared, for example, is a constant and is positive, and r is a constant, then it means the average power is precisely going to be equal to a half of the maximum power P naught. The average power is going to be half of the maximum power P naught. The average power is going to be half of either I naught, V naught, or half of I naught squared R, or half of V naught squared over R. That is going to be the average power. So what I'm saying is the average power, which you can write as that, is going to be a half of I naught squared R. Remember, this was the peak, or it is going to be a half of V naught squared R, or the average power is going to be, using the equation, which equation was that? Using the equation I naught V naught sine squared omega t, where the average of sine squared omega t is a half. So this will also be I naught V naught divided by 2 as the average power. So the average power will either be given by this, or that. So it's like the average power is not depending on the alternating current alone, it is depending on the square of the alternating current. The average power does not only depend on the alternating current, it depends on the square of the current. And of course, the square of the current is always positive. So the examiner will ask you to explain why there is power dissipated in a resistor even when the average value of alternating current is 0. So the power does not depend on the current, it depends on the current squared. And the square of a positive or negative value is always positive. So in a nutshell, I want you to note that the average power is half of the maximum power. The average power is half of the average. The average power is half of the maximum power. A few important things to note, having explored the average values of power, then we should now think about average values of current. But of course, we notice that the average value of current alone and the average value of voltage alone was 0. How about if we now consider the squares, because we know that the average value of a square was not 0. The average value of sine squared omega t is not 0. Then how about if we look at I being squared? So let's look at the squared values of current and voltage. If we consider current instead of considering I as being equal to I naught sine squared omega t, how about if we square this current? I need to change it to a very shiny color, maybe yellow. So how about if we square this current, and instead of getting the average, sorry, this is just I omega t, that is alternating current. How about if we square the current so that we have I squared instead, equaling to I naught squared sine squared omega t, and maybe later on we can find the average. We can find the square root. So in that case, if we consider this, we notice that if we find the average of I squared, it will no longer be 0. The average value of I squared is going to be, because average of sine squared omega t is a half, so this is going to be I naught squared divided by 2. In a similar way, if we consider voltage, alternating voltage is equal to V naught sine omega t. So if we square, we have V squared equals to V naught squared sine squared omega t. And if we take the averages, if we take the average of the square of V, so we have V squared average of V squared is going to be equal to V naught squared. The average of sine squared omega t is a half, so it is going to be V naught squared over 2. So it's like these averages, the average of the squared values are not 0, yet the average of I alone was 0. Perhaps we can take use, or we can employ these square values. So I have just showed that the average of I squared is equal to this, and the average of V squared is equal to this. So it means they are not 0. Then now we can take them back by trying to find the square root. Of course, we don't expect now the square root to be 0 if we try to find the square root. Now this will be called the root mean square values of current and the root mean square values of voltage if we try now to find the square roots. So imagine find the square root for I squared. So this will be I naught over root 2. The other one will be V naught over root 2. So taking the square root, we shall arrive at what we call the root mean square values, which will in exams many students write RMS. These are called the root mean square, or the RMS value of either current and voltage. That is, we shall have finding the square root of both sides will give us I naught over root of 2 when I find the square root of the first equation. And if I find the square root of the second equation for voltage, this will give me a V naught over root 2. Of course, when you press your calculator to find 1 over root 2, is going to give you 0.707. 1 over root 2 is 0.07 V naught. So we notice that when we find the square roots, we don't get 0. When we find the averages of the squares, we don't get 0. So it means that the square roots of these values are the most important values when alternating current is flowing through the wires. So we can agree that even though the average value of alternating current is 0, then what is causing an effect when alternating current is flowing through the wire might be the average values of the root mean square values. That is, the square root of the average values, the square roots of the values that we squared initially. Those values are going to be called the root mean square values of either current or the voltage. What are these values? When someone therefore talks about the root mean square values, we can argue that these are the ones which represent the effective values of current and voltage in any AC circuit. So when we say the alternating current flowing through a resistor is 2.5 amperes. If it is alternating current, then what we have mentioned must be the root mean square value. If we say the current flowing through the bulb, the alternating current flowing through the bulb is 2 amperes, then that value that I've mentioned must be the root mean square value because it is the effective current into that bulb. So the direct current with a value equal to the root mean square current, that is IRMS, of an AC circuit will produce exactly the same heating effect in a resistor. What do I mean by that statement? I'll explain it in more details. In specifying a domestic supply, it is the root mean square value that is quoted, not the peak value. So let me explain this in more details. When you go to buy a bulb, and they say the bulb requires 75 watts. What does that mean? Remember, at home, we are using alternating current. But when we say the bulb requires 75 watts, it means you can connect the bulb to a DC which supplies 75 watts. Or you can connect the bulb to an alternating current whose root mean square value gives a power of 75 watts. So this is going to be the average power. This is going to be the average power needed by that bulb if it is connected to an alternating supply. So if we say the bulb now needs 2.5 volts, this is not the peak voltage in the bulb. If you connect it to an alternating current, this is the peak value. But it means if I connect the same bulb to a DC which supplies 2.5 volts to light, if I want the same bulb to light using alternating current, the mean value, the root mean square value of current that will, the root mean square value of voltage that will light that bulb should be 2.5 volts. So that's why I said these values link the DC values, the root mean square values link the DC values to the equivalent alternating current values. So next time when you see a device labeled 2 amperes, this is not the peak value of current required by that device, but because most of the devices are connected to alternating current, it means for it to light, it should be connected to a power supply which gives a root mean square value of current equaling to 2 amperes. But of course, if I connect it to a DC supply which gives 2 amperes, it will automatically light. So it's like the DC values link or provide a direct link to the alternating current, or to the root mean square values link the DC values to the alternating current values. The root mean square values cause the same effect as the DC values. The root mean square current has the same effect in a resistor as direct current. The root mean square voltage will have the same effect or the same heating effect or will dissipate the same power in a resistor just like the direct voltage. Definition. Many times you open the past papers and you find a question asking you to define root mean square value. So what do we mean by the root mean square value? The root mean square value of, this time it could be root mean square value of current or root mean square value of voltage. So the root mean square value is the value of the alternating current if the examiner has asked current, or the value of the alternating voltage if the examiner has asked about voltage. That will produce thermal energy at the same rate as direct steady current or as DC or direct voltage in a resistor. It produces the same heating effect in a resistor just like direct steady current or direct steady voltage. That's what we call root mean square value. Remember, if it is current, you should concentrate on current, and if it is voltage, you should concentrate on voltage. That's what we call the root mean square values. To simplify this even further, it is the value of the direct current or the direct voltage that produces the same power or heating effect in a resistor, just like the alternating current. So it's like the root mean square values are those values of alternating current. They are those values which produce the same power in a resistor, just like the DC values. They cause the same heating effect in a resistor, just like the DC values. Those are what we call the root mean square values. Therefore, it is better for us to just simply say that the root mean square value links the DC equivalent values to the AC peak values by what we just mentioned as I. For example, I said I. Now I have to change the color here. For example, I said I root mean square is equal to I naught over the root of 2. And I said this value here has the same heating effect as a DC equivalent value. If the battery uses 2 volts, let's say the battery uses 2 volts DC, then for the battery, if the bulb uses 2 volts DC, then for the bulb to light, it will need 2 volts root mean square value. So it's like they have the same heating effect in a resistor, just like the DC values. Okay, so thus AC supply of a peak value of V naught. If you supply AC whose peak is V naught, then this delivers the same average power as a stated DC of value V naught over root 2. If the power supply has a peak of V naught, it will only deliver the same power as the direct voltage whose value is V naught over root 2. So this is, of course, the root mean square voltage. So we therefore call the DC equivalent values the root mean square values for AC. The DC equivalent values are what we call the root mean square values for AC. So you can't say power is equal to I times V for DC, and then you also say power is equal to I times V for AC, not at all. But I can say power is equal to I times V for DC, and I can say power is equal to I root mean square times V root mean square for AC, because the root mean square values are the equivalent values to the DC values. If I use this for DC, then I will use this for alternating current, because the root mean square values are the equivalent values to the DC values. Okay. For example, the average power could be given as I root mean square times V root mean square. So this is power because this is constant. In a device or in a resistor, of course, this is going to be average. When I multiply the root mean square value, the root mean square values, I'm getting the effective power in the resistor. For alternating current, it is always the average. So this will be the average power. Those are what we have discussed here are what we call the characteristics of alternating current. Those are the characteristics of alternating current. We talked about it being sinusoidal, we have talked about peak values, we have talked about root mean square values. Those are what we regard as characteristics of alternating current. Let's run through a few examples. Number 1. What is an alternating current? I think that is obvious. When we talk about alternating current, we are referring to current, an electric current that periodically reverses its direction in the circuit with a frequency which actually depends on the source. The frequency is independent of the constants of the circuit, but the frequency depends on the source. In other words, the frequency of a wave depends on a generator. Then we also talked about what we mean by peak voltage, that is V naught. Peak voltage, the maximum voltage, the amplitude of voltage, that's what we call the peak voltage. So peak voltage is the maximum voltage, it is the amplitude of voltage. Then we also talked about peak values and root mean square values. We have said the peak voltage is the maximum voltage. And then when we talk about the root mean square voltage, this is simply the alternating voltage that has the same heating effect in a resistor as a direct voltage. The alternating voltage which has the same heating effect in a resistor as the direct voltage. So if the peak voltage is written as V0, then the root mean square voltage, the root mean square value of voltage is written as V0 divided by root 2, which means V0 is greater than the root mean square, the peak is greater than the root mean square value. So to distinguish these two terms, I'll give 3 important points. Number one, the peak voltage is the maximum voltage, yet the root mean square voltage is the alternating voltage that has the same heating effect. In other words, dissipates the same power. Dissipates the same power in a resistor, just like a direct voltage. And since the peak voltage is V0, yet the root mean square value of voltage is V0 over root 2, it means the peak voltage is greater than the root mean square voltage, the root mean square value of voltage. Okay. Example number 4. What is meant by frequency? Of course, frequency, that one is the number of complete cycles occurring per unit time or per second. Then the root mean square current, of course, that is going to be the alternating current that has the same heating effect in a resistor as direct current. The alternating current which dissipates the same power in a resistor as direct current. So it has the same heating effect, to be precise. Then for an alternating voltage, V equals to 20 volts sine of 200 pi t, that is in milliseconds, t is measured in milliseconds, determine the peak. So I just compare V equals to 20 sine of 200 pi times t. I'm comparing this with the V equals to V0 sine omega t. So when you compare, you notice that V0, which is the peak, is 20. Then the root mean square value. Of course, for the root mean square value, I will say V root mean square is equal to V0 divided by the root of 2, which is going to be 20 divided by root of 2, which I think this is correct. Then the frequency. Of course, we know that omega equals 2. Okay, for the starters, omega is 2 pi over t. But remember, 1 over t is frequency, so this is the same as 2 pi times f. Why do I bring in frequency? I don't need, okay, we need the frequency, sorry. So this is 2 pi f. So omega is 2 pi f. So to find the frequency, I can simply say that frequency is going to be omega, which omega, when I compare the equations, omega is 200 pi. So this is going to be 200 pi divided by 2 pi, which gives us 100. So I think these answers are going to be correct. Question 6. An AC supply is connected to a resistor. When the peak value of the EMF of the supply is V0, the peak value is V0, and the frequency is F. The mean power dissipated in the resistor is P. So the mean power dissipated in the resistor is P. The supply is then changed to twice F. The peak value of the EMF remaining as V0. What is now the new power in the resistor? I don't think the power is depending on the frequency, because the mean power dissipated in the resistor is not depending on the frequency. Since they gave us, we have resistance, they have given us V naught, and they have talked about resistance. So the average power in a resistor is equal to a half of P naught, where P naught is the peak power, the maximum power, which is equal to, it can be V naught squared divided by 2R. Now, I don't expect anyone to ask me why is it P naught squared over 2R, but I will still do this after all. Sorry. So, of course, we have already mentioned, since we have resistance and we have V naught, we have already mentioned that the peak power is equal to either I naught times V naught, or it is I naught squared times R, or it is V naught squared divided by R. I just modified the DC values. So that is the peak value. The average is half of the peak. So it means the average value of the power, because they have talked about a V naught and the resistance, so the average is simply going to be V naught squared divided by 2R. And this is not depending on the frequency at all. So whether the frequency is doubled, the average power is going to remain the same because it is independent. It is independent of the frequency. So this is not depending on the frequency, so I'll simply say independent of the frequency. So it is going to be the same because it's independent of the frequency. So a 1.5 kilowatt heater is connected to a domestic supply, which is quoted as 240. So the domestic supply is quoted as 240 volts. And remember, I mentioned that what is quoted is not the peak, is actually always the average, or is not the average, the root mean square value. What is quoted in domestic power supplies is actually the root mean square value. So calculate the peak current in the heater and its resistance. Okay, I don't have enough space, so I have to use this part here. So we want to find the peak current. What has been given is 1.5 kilowatts is always the average power in the domestic heater. And what is given here, this is going to be the root mean square value. So we know that the average power is equal to the root mean square current times the root mean square voltage. V root mean square times I root mean square. That is the average power. So if I try to find the value for the peak current, I can first find the root mean square value of current. So I root mean square is going to be the power, which is 1.5 times 10 to the power of 3 divided by the root mean square value of voltage, which is 240. I said domestic power supplies, whatever is quoted is always average power and the root mean square values. So this is going to give me the root mean square value, which is, let me press my calculator, 1.5 exponent 3 divided by 240. So this is 6.25. So 6.25 amperes, that is root mean square current, but we want to find a peak current. You should also remember that the root mean square current is equal to the peak current divided by the root of 2. So I'm going to multiply this by the root of 2 to get the peak. The peak current is going to be root 2 times 6.25. So this gives me 8.8. 8.8 amperes. So that is 8.8 amperes approximated to two significant figures. That is going to be the root mean, the peak value of current. Then the resistance, I don't have enough space, but I will try to use this point here. The resistance, of course, I can use still, this is the root mean square value, and I have the root mean square current. Of course, therefore I can use Ohm's law and then modify it in terms of root mean square values. So it means V root mean square can also be equal to I root mean square times the resistance, which means the resistance would be equal to V root mean square, which is 240, divided by I root mean square, which is 6.25. Or you could use a power equals to V squared root mean square over resistance. You could still find that is average power. V squared root mean square over resistance, where you could make R the subject and find the answer. So 240 divided by 6.25. So this would be 38.4 ohms as the current, the resistance. Okay. A heater of resistance 40 ohms is connected to a domestic supply quoted as, I can't see this, so I have to delete what I've just written. A heater of resistance of 40 hertz, maybe I should write the answer here because, so here we have seen the resistance is 38.4 ohms. I've calculated that. So a heater of resistance 40 ohms is quoted to a domestic supply. Is connected to a domestic supply quoted as 240. I said this is root mean square, so this is V root mean square. Then calculate the average power in the resistor. So they have given us the resistance and they want us to find the average power. So the average power is going to be equal to, I'm going to use an equation which has resistance and V. Instead of saying power is equal to V squared over R, I'll instead say it is V root mean square squared divided by R. So you just divide. V root mean square is 240 squared divided by R, which is 40. So this gives us the average power. 240 squared divided by 40. And this gives us 1440 watts. So this is going to be the average power. Notice how I modify the DC values when I'm calculating with AC values. When we say average power, or even when I say power in a resistor, when I'm talking about alternating current, in your mind, the first thing to come into your mind should be it is average power, because what is quoted, what is effective in a resistor is actually average. That's what is effective. It's always average. Okay, then as we want to find what is the maximum and minimum values of the instantaneous power in a resistor. Of course, minimum power is automatically 0, because if you look at the equation of instantaneous power, power is equal to, let's say, V naught squared over R sine squared omega t, if I use that equation. When t equals to 0, the power is going to be 0. Then when t equals to any other values, the power will vary up to when it's sine squared omega t equals to 1, the power will be maximum. So the minimum power is going to be 0, and the maximum power will be equal to V naught squared over R, which is the same as V root mean square squared over R. So minimum power is 0, and power maximum P naught is going to be twice. It is actually twice the average power. which is going to be 2,880 watts. If the average power is half of the maximum, then it means the maximum power, if the average power is half of the maximum, then the maximum power is twice. The maximum power is going to be twice. Alternatively, if you don't want to use that, you can check. We have maximum power occurs when sine squared omega t is equal to 1. So maximum power is going to be V naught squared divided by R, which is going to be V naught squared. Remember, V naught squared is equal to the root of 2 times V root mean square, because V root mean square is V naught over root 2, but this should be squared. Then I divide this by R. V naught squared, because V naught is root 2 times the root mean square. So I'm now trying to substitute here. This is going to be root of 2 times V root mean square was 240, but remember this should be squared. Then I divide this by R, which is 40. So I can press my calculator. So I have root of 2 times 240. Then I square that and I divide this by 40. So this gives me 2,880 watts. So any other formula, as long as you use it carefully, you will arrive at that correct answer. A sinusoidal PD of peak value 25 volts is connected across a 20 ohm resistor. What is the average power dissipated in the resistor? We want average power dissipated in the resistor. So remember the DC values first. Before you relate to this, remember the DC values. If we were dealing with DC values directly, and you want to find average power dissipated in a resistor, then you would precisely say that power dissipated is equal to V squared over R if it was direct current or direct voltage. But here they have quoted for us peak, which means they were dealing with alternating. So it means the average power is simply going to be V root mean square, but squared, divided by R. Of course, there is nothing like R root mean square, not at all. So we also know that V root mean square is the same as V naught, which is the peak value, divided by root of 2. So it means where there is V root mean square but squared, I'm going to put there V naught over root of 2. So when I substitute this into this, by the way, when I square both sides, this becomes V naught squared divided by 2. So when I substitute for V root mean square squared, the average power becomes, the reason as why I'm substituting is because they gave us the peak. They didn't give us the root mean square, they gave us the peak and the resistance. So this is going to be V naught squared divided by 2. So it is V naught squared over 2R. So this is going to be 25 squared divided by 2 times R, which is 40. So which is 20. So 25 divided by 40, I think that is 25 squared divided by 40. So this is giving me 15.6. So that is 15.6 watts as the average power dissipated in the resistor. I want you to note that if we had used V naught rather than V root mean squared directly, then if I had used V naught, if I had used V naught directly here, I would say power is equal to V naught squared over R, then I would get a different answer, which would actually be, it would actually be twice, I think. It would be twice. And that would be the maximum power instead of being the average power. That's why this 2 in the denominator here takes you back to the example that we have done here. Where there is no 2 here, we are finding the maximum power. This 2 here is because the average power is always half of the maximum power. That's why in the first example, in example 8, I got the maximum power by multiplying 2 times the average. And I got 2,880, which I used a different method, and I got the same answer here. So it's the same thing. The mains SC supply in some countries is 110 volts root mean square at 50 Hertz. What is the peak value of the voltage? So this is direct. We said V root mean square is V naught over root 2, so the peak value V naught is equal to root of 2 times V root mean square. So it is root of 2 times 110, which is root of 2 times 110. So this is 160 or 156 volts. What is the peak to peak value? So peak to peak is of course twice this. V naught upwards, V naught negative V naught downwards, so the peak to peak is twice. So it is twice V naught. So I just multiply this by 2, which is 311 or 312, I think. Let me see, 156 times 2. 312 volts. Then how long does one cycle of this SC supply last? So period is 1 over frequency. I think 1 over 50 is 0.02 seconds. A 100-watt lamp is designed for use with 110 volts SC. Remember I said whatever is quoted is root mean square. So they have said 110 volts SC, that is root mean square. What is the resistance of the filament? So the power which is given is always average power. So the average power can be, since we have V, remember the DC equations, all of them, P is equal to I times V, P is equal to I squared times R, P is equal to V squared over R. So you just modify them when you're dealing with the power, whatever you're calculating is average power, just modify them to include the root mean square values. So since I have the average power and I have the root mean square value of V, then I'll use the last one. So this is going to be equal to V root mean square, but is squared, divided by R. So I want to find, I'm trying to find the resistance. So it means I'll simply say the resistance R is going to be equal to the power, which is 11100. So that's wrong mathematics. I'm making R the subject, so R is going to be V squared, which is 110 squared, divided by average power, which is 100. And when you press your calculator, so this is equal to 121. watts. Okay, I think that is fine. Why are there so many questions? So which will light a lamp more brightly? Is it a 12? Is it a 12 volts peak AC or a 12 volts steady DC? I always ask my students such a question just to check if they have understood what I mean, what we mean by, or what the implication of root mean square values is. So we have 12 volts AC and we have 12 volts steady DC. This one is DC. So this one here is not what is effective in the lamp. We have to find what is effective in the lamp. So what is effective in the lamp for 12 volts peak is the root mean square value. So for AC, for alternating current, the root mean square value is the effective voltage in the lamp. So this is equal to V naught divided by root of 2, which will be 12 over root of 2. And 12 divided by root of 2, 12 divided by root of 2 is 8.5 volts. So I want you to notice that 8.5 is the effective voltage in the lamp. It is less than 12 volts. So it means the 12 volts steady DC is going to be brighter. The 12 volts steady DC is going to be brighter because 12 volts peak AC is equivalent to 8.5 volts DC, which is less than, sorry, which will light a lamp more brightly. Is it a 12 volts peak AC or 12 volts steady DC? So it is going to be 12 volts steady DC because 12 volts peak AC, the effective voltage is going to be 8.5, which is less than 12 volts. So this is going to be, so it means 12 volts AC, I mean 12 volts DC is going to be brighter. 12 volts steady DC will light more brightly. So the 12 volts steady DC will light more brightly. Okay. UK means AC has an RMS value, that is root mean square value of 230 volts and a frequency of 50 hertz. Sketch a graph of voltage against time for one cycle. So to sketch a graph of voltage against time for one cycle, we have to first of all find a period to be able to sketch this. Since they have given us the frequency, the period is going to be period using this frequency here. The period time for one cycle is going to be 1 over 50, which I think is going to be 0.02 seconds. Then we need to find the peak because they gave us the root mean square value. So for the peak, I'll use this value here. The peak voltage is going to be equal to the square root of 2 times the root mean square value, which is 230. I think this is 300 and something. So root of 2 times 230. So this is approximately 225. I mean 325 volts. That is the peak. So to sketch a graph, you must have the peak and the frequency. You can try to sketch this, but I'll just sketch. They want just one cycle of the AC, include the peak values, voltage, and the period. So I'll sketch this easily. You can sketch a better graph. So this is going to be voltage against time. So the peak voltage is 325. Of course, it varies. Oh, sorry, this is alternating, so I have to add a negative part here. Let me try to reduce this. So the peak should go up to 325 upwards and negative 325 downwards, because that is the peak, and this is alternating voltage. So this is a graph of voltage against time. So if we can consider t at t equals to 0 to be 0. I'm going to break the time into 4 parts. When t equals to 0, when t equals to a quarter a period, when t is equal to a half a period, when t is equal to 3/4, and when t equals to 1 period. Of course, if t equals to 0, v is 0. When t equals to a quarter period, v will be maximum, back to 0, maximum, back to 0. So it is going to be a sine curve because this is sinusoidal. So they said include the time period on the axis. So this is, of course, here it is 0.02. Here it is going to be 0.01. You can put here 0.005, 0.015. As simple as that. You can sketch a better graph. But if you are doing paper 4 and you passed AS or you have finished AS, you must be having good graphical knowledge at this point. Okay. What is the ratio of powers delivered by 20 volts DC and so we have 20 volts DC and 20 volts peak AC to the same load, that is the same resistor. Let's begin with, of course, for 20 volts DC, the power for DC, I'll start with DC. For DC, the power delivered is going to simply be V squared over R, which is going to be 20 squared over R, that is for DC. But then for AC, the power is going to be the average power, which is going to be V squared, but this is going to be root mean square over the resistance R. And remember, V root mean square is root 2 times V naught. So this is root 2 times V naught, but this should be squared. No, not root 2 times V naught, it's root 2 over. V root mean square is root 2. Okay, where should I write? V root mean square is equal to V naught over root of 2. When I square, I will square both sides, so it means the power here, which is actual average power, is going to be V naught over root of, when I square, the root goes off, so it becomes 2 times R, but this is squared. So this is going to be V naught squared is 20 squared divided by 2 root of 2, 2 times R, which is the same as, now I want to find a ratio, because the question wanted us to find the ratio. So the ratio of power delivered by the DC, which is 20 squared over R, divided by, so I would get the reciprocal, divided by the power delivered by a 20 volts peak AC, so it will be 2R over 20 squared. So this one cancels, R cancels. So it means it's going to be 2. So the ratio is going to be 2. In other words, the power delivered by DC is actually going to be twice the power delivered by 20 volts peak AC. Okay. Determine the mean of the curves shown below. Of course, these are easy curves. This is alternating voltage. If I get this part here, which is positive, plus this part here, which is negative, when I sum up, I have positive V naught plus negative V naught divided by 2. This gives us 0. So here the average value of V is equal to 0 for alternating voltage. Then for power, you saw that the graph of power is always above the x-axis, is above the 0 axis. So the average power is actually going to be half of the maximum power. So this time axis is supposed to be here. So the average, if this is power, we know that the average value of power, is going to be equal to P naught over 2. I think this graph is wrong because the graph of power against time cannot be below the x-axis. So this time part is supposed to be at the bottom here. I think that was a typing error. So the average power is always P naught over 2. It can never be 0 because we said power is equal to I times V. I and V are always in phase. When I is positive, V is positive. The product is positive. Or power is equal to I squared times R. Whenever I is squared, it is always positive. Or power is equal to V squared over R. Whether V is positive or negative, power is always positive. So the graph will always be above the x-axis. So the average is going to be the maximum divided by 2, as we have already seen. Sketch a graph of an alternating current of an amplitude 20 amperes, 50 hertz, and a phase of pi over 2 radians. What's the equation of the graph? Of course, this is amplitude. Because it's alternating current, I'll just sketch this one here. I'll just sketch one cycle. I'll not mind about the phase at this level, so t equals to 0. Frequency is 50 hertz, which means the period is 0.02 seconds. So 0, this is 0.1, that is half. Means 0.01, that is half. 0.02, that is one cycle. So this is 0.005, 0.015, that is a quarter cycle. So the peak is 20. So I'll put 20 up and negative 20 down. This is positive current against time. So this sketch will simply be like this. And so on and so forth. What is the equation of the graph? Of course, the equation is I equals to I naught sine. So this is going to be omega. Remember, this is frequency. I need to find omega. Omega is 2 pi times f. So this is going to be 50 pi. Sorry, not 50 pi, 100 pi. 100 of pi, that is omega. So I'll write here 100 pi times t, but they added a phase difference, so I will simply say plus pi over 2. But this part of phase difference is not very important at this level. So it is I equals to I naught sine 100 pi t plus pi over 2. This is just pi over 2 is just the phase difference. I just added it there, but it's not very important at this level. Consider the graph below. Which questions are on this graph? What is the value of the current I when time t is 5 milliseconds? When t is 5 milliseconds, so you just look for 5 milliseconds. I think this is direct. You just look at the graph there. It is 2 amperes positive. At what time does the current next have the same value but negative? So you can look at 15 milliseconds. Next, at what time does the current next have? So that is just at 15 milliseconds. Okay, where I give so many examples here. What is the time t for one complete cycle? Of course, from the previous graph, time for one complete cycle, the period is 20 seconds, 20 milliseconds. Time for one complete cycle is 20 milliseconds. Time for one complete cycle is 20. Of course, the period is 20 milliseconds. Maybe they may ask us for the frequency, which is 1 over 20 times 10 to the power of minus 3. The frequency, let's just calculate the frequency, 1 divided by 20 exponent minus 3. I think the frequency is 50 hertz. They may also ask us to find the peak value of current, I naught. What is the current when t is equal to 5? So I naught is equal to 2 amperes. That is the peak current. In case they ask us for angular frequency for this equation, omega is going to be equal to, we have the period, so omega is 2 pi over t, which is going to be 2 pi divided by t. T must be in seconds, so this is 20 times 10 to the power of minus 3. So 20 divided by, I want to take this upwards, so this becomes 2000 divided by 20 times pi. So omega is going to be equal to 100 pi radians per second. Then suppose they want us to write the equation. Because it is current, I'll say I equals to where there is I naught, where there is, oh, by the way, this equation, the first equation, I would have modified it to be I equals where there is I naught, I was supposed to put there 20 sine of 100 pi t plus pi over 2. So even here where there is I naught, I'm going to put there 2 sine of where there is omega t, I'm going to put there the value of omega, which is 100 pi, then times t. So this will be the equation required, I think, if they ask for the equation. So let's see what questions are there. So they wanted the period, we have verified that. They wanted the frequency, we have calculated that. They wanted the value of I and omega, we have calculated that. They wanted the equation, we have also done that. So that is covered. An alternating current measured in amps is represented by that equation. I equals to 5.0 sine 120 pi t, where the values for this current, for this current of I naught, omega, and F. So what are the values of this current? I naught, omega, and F. So we just compare I equals to 5.0 sine 120 pi t with the general equation I equals to I naught sine omega times t. So it means I naught is going to be 5 amperes. Omega is going to be 120 radians per second. Then what else? F, frequency. We know that omega is equal to 2 pi over t, which is 2 pi f. So this is going to be 2 pi times, f is going to be equal to omega divided by 2 pi. So which is going to be 120 divided by 2 pi. So this is going to be 120 divided by 2 pi. So omega is approximately, f, the frequency is approximately 19. The frequency is approximately 19. Oh, omega was 120 pi. There's a pi here. So if it is 120 pi, then the pi cancels, so this becomes 60. 60 hertz, sorry for that. So that is 60 hertz. Then sketch a graph to represent the current. Oh, what is the period? Of course, period is equal to 1 over f, which is 1 over 60. What is 1 over 60? 1 divided by 60. This is 0.0166 recurring, or 0.17, or which is approximately 17 milliseconds. Okay, so you sketch a graph. So to sketch the graph, I'll sketch the graph here, a small sketch of current against t. So I have to come up with I naught on both sides. So this is positive 5 and we have negative 5. So I have a quarter cycle, half a cycle, 3/4, and 1 complete cycle. So at t equals to 0, I can say I is 0, so it doesn't matter. So I'll have such a graph. Where this will be 17. This is time in milliseconds, current in amperes, so this is 17. You can divide this by 2, 17 divided by 2. This could be 8.5 here, and so on and so forth. So that will be the sketch. I've just sketched one cycle. You can sketch more cycles. An alternating voltage V in volts is represented by the equation. So what are the values of V naught, omega, and F? So you just compare with V equals to V naught sine omega t. So it means V naught is 300 volts. That's number one. Then omega is going to be 100 pi in radians per second. Then frequency, we know that omega equals 2 pi times f. So f is going to be 100 pi divided by 2 pi. So f is going to be 50, I think. 50 hertz. What is the value of V when t is equal to 0.002? Okay, so I will find that here using V equals 300 sine of 100 pi times t, which is 0.002. Your calculator should be in radians. When you because there is a pi here, your calculator should be in radians. Okay, so this is giving me 176 volts. Then sketch a graph to show two complete cycles. So the peak should be 300. The peak should be 300. and the period the peak should be 300 and the period should be because the frequency is 50 hertz, the period is 1 over 50, period is equal to 1 over 50, which is 0.02 seconds. Okay, so I'll just sketch this briefly. It is a brief sketch. So this is a graph of V against t in seconds. So we want 2 complete cycles. So let's say the first cycle stops at 0.02. The second cycle is going to stop at 0.04. In between here, we have 0.03. We also have 0.01. Of course, a quarter cycle, that is 0.05. So I'll sketch my graph briefly. Where the peak is going to be at 300. Okay, so those are the 2 cycles. So now these ones, I think now you can try out what is the root mean square value of an AC represented by that equation. Of course, you notice that this is V naught, so you can be able to find the root mean square value because we know that I root mean square is equal to I naught divided by root of 2, that is direct. The main supply to domestic consumers in many European countries has a root mean square voltage of 230. What is the peak value of supply? So we have the root mean square. We should be able to find the peak value, V naught. Root mean square equals to V naught over root 2. What is the average power dissipated when the sinusoidal alternating current with a peak value of 3 amperes flows through a resistor of that? So the average power, remember, is going to be the V root mean square, but squared divided by R. But remember, V root mean square is equal to V naught divided by root of 2. So you should be able to get that. A sinusoidal voltage of peak value 325 volts is connected across 1 kilo ohm resistor. So they have given us the peak. What is the root mean square value? V root mean square equals to V naught divided by root of 2. Use V equals to IR to calculate the root mean square current which flows through the resistor. So it means V root mean square is going to be I root mean square times R. So you should be able, since the resistance is known and V root mean square is known, you should be able to get the root mean square current. And what is the average power dissipated? So we know that average power is going to be I root mean square times V root mean square, or you can get I root mean square squared times R, or you can get V root mean square squared divided by R, and so on and so forth. That will give you the average power, or you can get the peak power times 2. I mean the divide by 2. I think that should be the end.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you.